Hi, I'm Michael, a PhD student at UC Santa Barbara, and this is my presentation for EACL 2023, PECO, Examining Single Sentence Label Leakage in NLI Datasets through the Progressive Evaluation of Cluster Outliers. So first of all, I'm going to provide a little teaser on what we'll be talking about in this presentation. So if you're familiar with NLI and the leakage problem, what I'm going to show is a technique that allows us to automatically find shortcut feature biases that allow for successful single sentence classification of a sentence pair that actually get learned by models when they're trained on a given data set in the paired sentence condition. Okay, so now for the rest of you, I'll give a recap on what NLI is. So NLI is the task where we want to predict a relation label from a pair of premise and hypothesis sentences. Now this relation label can take three values: entail, contradiction, and neutral. This task is useful as basically a piece of middleware where, for example, you could analyze the outputs of LLMs at scale. That's one task I'm interested in. But unfortunately, many benchmarks for this task have fundamental flaws. So the first problem is that these tasks are often, so the first problem is that these benchmarks are often saturated. So what does that mean? A saturated benchmark is one that, in short, models are able to perform very well on. To make it more precise for NLI benchmarks, this means high test set performance when trained on an in-distribution training set. Saturated benchmarks are a problem. First of all, they make it hard to track future progress. And also, in the case of when you're trying to use them to actually produce a model that you can put in a downstream system or use to analyze something, it could be evidence that the dataset isn't actually expressive enough to capture the logical relation that underlies the thing you're really looking for. The second, and in my opinion more important problem, is that of single sentence label leakage. So what is this? Well, first a bit of terminology. We use the term paired sentence condition, or PSC, to refer to the standard NLI setting where a model is inferring the label from the aforementioned three based on both the premise and hypothesis sentences. However, you can also test a dataset and model pair using just the single sentence condition, where a model is only predicting the label based on the premise or hypothesis alone. Now, in principle, this should be impossible because NLI datasets are supposed to be modeling a logical relation between both sentences. However, previous results have already shown that many NLI datasets actually exhibit what we call single sentence label leakage, or high performance in the SSE. So the first research question is, do modern datasets also do this? In order to answer that, we want to plot every single dataset along this idealized pair of axes, where we look at both the single sentence accuracy and the paired sentence accuracy that are achieved by our replication models. Rightward location on the x-axis means that a dataset is more biased and exhibits more single sentence label leakage, while y-axis positivity means a benchmark is more saturated. So we can place any NLI dataset we want to test based on these two axes, and our goal is to find one that lands in this optimal benchmark zone, which is both not saturated and does not exhibit this single sentence label leakage. So let's see how bad the single sentence label leakage problem is on current datasets. In order to test this, we replicate the state-of-the-art performance based on paired sentence condition accuracy using a simple Roberta baseline. This leads to results for every single dataset where we look at the paired sentence condition accuracy, the single sentence condition accuracy, and the majority voting accuracy. If you just guess the majority label in the dataset, how accurate will you be? And what we find is that for the 5 datasets that have already had this problem analyzed on, we see exactly the expected thing, that they all are quite saturated and also have surprisingly high single sentence condition accuracy. The next cluster of datasets that we analyzed for this are the ANLI family of datasets. These were produced using an adversarial human-in-the-loop process where they tried to augment samples in specific regions to make it as hard as possible for a classifier. They did this in 3 steps, which we have marked as ANLI 1, 2, and 3. And an interesting thing that we found is that although the paired sentence condition accuracy goes lower and lower as we move through those subsets, the single sentence condition accuracy actually gets higher and higher. So these datasets, through this adversarial process, actually start expressing more and more stereotypically hard to classify things in the paired sentence, but situations where the model can cheat very easily in the single sentence condition. The next family of models that we consider in this analysis are XNLI and original Chinese NLI. The thing that's different about both of these is that XNLI is a multilingual NLI benchmark based on MNLI that consists of only a test set, where samples are directly translated from the MNLI test sets into a litany of other languages. The interesting thing that we find here is that the single sentence condition accuracy generalizes quite well, even though in order to produce a model for XNLI, you train a multilingual encoder on just MNLI. What this means is that the single sentence condition biases that are leading to these cheating features really are semantic in nature, and they go deeper than raw lexical, or they're still expressed lexically, but they exist on a fundamental semantic level that carries across translations into multiple languages. Thought that was pretty interesting. And then finally, we look at some data sets that were produced even more recently with an eye towards being debiased. And unfortunately, what happens when you produce these debiased data sets is even if we can reduce the existence of single sentence condition accuracy on, let's say, the hypothesis distribution, these interventions often lead to introducing biases on the premise distribution or vice versa. So this is a challenge that has to be overcome. So here's where all of these data sets lay in that same pair of axes that I saw before. So some of them are getting a little bit close to the optimal benchmark zone, but in general, these data sets are pretty easy often and often still exhibit significant bias. So really we would like to go further with this. So here's the question, how do we do this? Well, first we introduce a couple of metrics that allow us to more closely analyze this single sentence condition leakage. So the first one is just a simple delta. How much of a performance improvement do we see in the single sentence condition over the majority guessing strategy? The second one that we look at is the ratio of performance in the single sentence condition to performance in the paired sentence condition. Additionally, in addition to those dataset level metrics, we can look at sample level metrics that are analyzing the SSC leakage itself. The first one is the sample-wise decision agreement in terms of sample level. So for each output in the model, do the SSC model and the PSC model agree? Yes or no? Additionally, we can look at agreement in terms of token relevance, where we take the cosine similarity of the sample-wise normalized local explanation vector produced in prior work. So how do these metrics correlate? First, we find that the closer SSC and PSC performance are, the more correlated the model's sample-wise decisions will be. In other words, this positive correlation we find between this %RR and NBA metrics. Additionally, we find that models do use the cheating features to actually avoid learning the desired reasoning. We base this assumption on the correlation that we find between overall SSC accuracy and token relevance agreement. In other words, the more accurate a model is in the single sentence condition, the more likely it is that in the paired sentence condition, the model will agree with the cheating feature model. The paired sentence condition model will agree with the cheating model on its decisions. And finally, as an analysis tool, we introduce the progressive evaluation of cluster outliers, or PECO. The purpose of PECO is to assess the degree to which a model that's trained in the paired sentence condition is using cheating feature information that's visible in the single sentence condition, thereby reducing the validity of the benchmark. To do this, we perform 4 steps, which overall are intended to cluster single sentence condition samples using a model that's trained in the paired sentence condition. So first, we collect what we call biased condition embeddings by masking one of the sentences in the sentence pair, then feeding it in to the paired sentence condition model and extracting embeddings using PCA through the fully connected layer. We then identify local regions by applying a high-end k-means clustering onto those embeddings. We then compare each cluster's label distribution locally to the global label distribution, which allows us to identify outliers by integrating under a curve of each cluster's label-wise divergence score. This gives us one single number for the overall biasness of the data set. Additionally, we can use the clustering itself to identify the regions that exhibit high bias in the paired sentence condition. So what this is showing is the t-SNE projection of that embedding space. We've highlighted with large markers examples of regions that have a bias over some arbitrarily chosen threshold of L2 score. And what we find is that as we raise the L2 score for indicating bias, the clusters that exhibit bias grow to take up more and more of the overall space. And the interesting thing is that these clusters are separated out from a model learned in the paired sentence condition. This seems suggestive to us that information that is useful in the single sentence condition for cheating and classifying samples is actually employed by models that are trained in the paired sentence condition. This in turn allows us to look at the metric correlation of this normalized PECO score against that same accuracy ratio. And we indeed find that decreased PECO score correlates with a wider gap between the paired sentence condition and single sentence condition accuracy, with a PCC of 64. This should be very useful for future work, as it implies that interventions that forcefully lower the PECO score are likely to additionally directly lead to a decrease in the single sentence condition accuracy. This can be used in the future to produce debiased benchmarks and better NLI datasets that can hopefully be used to produce more useful tools for actually understanding entailment between pairs of sentences in a generalized setting. So thank you for watching my talk. There's a demo online at my website, saxon.me/PECO, and you can also find me on Twitter at m2saxon. And this QR code is a link to the archive copy of our paper. Please check out the demo. Hopefully you'll find it entertaining. Thank you.